Alright, welcome to the second repeat class of Controls 3020, 26 Winter, Controls 2, Venture College, London, Ontario. January 28, 2026. Beautiful winter. Picture winter. Postcard type of a winter. I just took a picture. Anyways, let's start this lesson here. And today's lesson is brought to you by the letter. Oh, no. F5. Oh, let me just make sure that I didn't stop anything here because I pressed the wrong F key. No, we're still recording. Okay, cool. Alright, so we have our presentation. F5 is to start the show. And we have the coolest, the latest technology animation going on. It's almost 3D, but when it grows up, it's going to be 3D. See what's happening here? It's a relay kicking in and out. So what do we have on this wonderful high-tech animation of a relay? We have the relay or the coil contacts right here. Let me just get my laser pointer. That's where the DC is applied, and usually we have 24 volts. That's a common working for the controls, common working 24 volts DC. And yes, we're applying DC voltage into a coil. That's how solenoid works. Once we apply the DC current into the coil terminals, then magnetic field is being created, making a magnet of whatever is stuck inside that coil, a metallic rod. It's magnetized momentarily as long as the magnetic field is present, and the magnetized rod pulls the metallic part of the pole of the switch, and the switch is being brought back to a monostable state by a spring, but it overcomes the spring pulling back action, closes that, and current flow. Everybody happy. Okay, so then when power is being interrupted to the coil, this electromagnet becomes not a magnet. It's just sitting there unenergized, and the spring has the ability to pull the contact back, and the contact is disrupted. So this way we could have a pilot signal, small amount of power, controlling something huger, right? Something really big, depending on what the rating of the contact is and whatever the application of this thing is. But in a way that this, whatever the circuitry is here, is physically independent of the contacts that are being worked on here. So we have a relay, so we have a solenoid, so we have a solenoid trigger, we have a solenoid actuator. If we install that into some sort of a valve, well, we could also make a solenoid with a plunger. We can move things. So the whole thing, the solenoids and relays, they work on a very similar principle. Well, it's Faraday's law, all of it, right? And Lenz's law. Now, the letter, was brought to you by a letter EMF, by 3 letters, and by the protection diodes and, in relays. Okay. All right, cool. Here's the opening statement and a half. Now, when it comes to relays, we need to be aware of certain things. We need to know how to use them, what to do, what not to do, right? And what to be careful of, and how to troubleshoot, and how to install and design things so we can design a certain type of equipment that works for us, not against us. Right? As we go along, it will all become clear. All right. EMF, the idea of EMF, I'm just going to scratch the surface of that because you will be studying that in the machines course when you do the motors and generators. However, I also have a link if you want to kind of get a head start on that. You can click on my link. There's a video on talking about EMF and back EMF with the synchronous machines. That's way back when I was teaching the electrical machines. Sometimes they give me that course. Anyways, so electromotive force is that's the acronym for EMF, is the voltage generated by a source. My board. Where's my board? Here's my board. Alright, I'm going to start from scratch. Erase this whole thing. Alright, we have a power source, a longer prong, shorter prong, and we have some sort of a conductor, and that conductor is connected to a load, and that's a resistor, and that, here, make things connect. It goes back to the power supply. Forget the switches, forget fuses. It's just a hypothetical circuit, simplest circuit. Of course, the longer prong of the DC power supply is the positive. The shorter prong is the negative. And if we assume the conventional current flow, we're going to have the current flow from the positive part of the power supply leaving the power supply, going through the rest of the circuits, is going to flow through the resistor that we are going to call it R, and this power supply we're going to call it E for EMF supply. All right, and the current, of course, is going to come back here. So we're going to talk about a couple things: EMF and a voltage drop. EMF the unit for EMF is volts, and I always put unit in square brackets. That's just me. Now the voltage across the resistor is also going to be, or it is, in volts. So both EMF and the voltage drop across the load, in this case a resistor, we both measure that in volts. The two main differences between these two devices, or one major difference, is that this device here has a voltage across it, and this device has a voltage across it. But this is a source of the voltage, and this is subjected to the voltage that is being introduced by the source. So we have the electromotive force here measured in volts supplying the voltage, and we have a voltage drop receiving the voltage from the source. Electric field is going to point towards the positive in the EMF in the source, so that's the electric field, and it's going to point in the direction of the current here. So the current in the load, through the load, flows from the conventional current, flows from the positive, the more positive terminal, to the more negative terminal in the receiver, in the load. But in the source, inside the source, through the source, conventional current flows from negative to positive because, well, the directionality has to be preserved. Right? So that's how the current flows through this whole circuit. Here it goes through that, and it goes through that way. Okay. Now, so the electric field is going to point with the direction of the current flow. And also when we have a DC or AC current, but let's talk about the DC right now. AC is also going to cause a magnetic field, except it's going to be pulsating, collapsing, and going other way. But with the DC, we're going to have a steady magnetic field spinning around the conductor in this sort of a way. You see, remember the corkscrew that we had? Here's a corkscrew. All right. Used to open the wine bottles. It's a crooked corkscrew. When you turn it this way here, that thing is going to move that way. So here's the direction of the current, and here's the direction of the corkscrew turning, which would be the direction of the magnetic field spinning. Or you can use the right hand rule, but I like the corkscrew better. There. So we have, when the current flows, when the circuit is on, we have an electric field being present, because it's the tension, is the electric field with the movement of the electrons or the charges, because the electrons would shift that way in the electron flow, what's really happening, and by the same time the so-called positive charges are moving the other way, right? So there, okay. And when the current flows, we have electric field being present, and when the current flows, we have the magnetic field being present. The magnetic field is caused by the current flow. When the current stops flowing, if we interrupt the circuit, where's my eraser? Here. If we interrupt the circuit right here, we open a switch, if there's a switch here, then, excuse me, I'm talking too much. It's my second time talking, second hour. Sip of coffee, excuse me. All right. So the electric field is still going to be present because the tension is going to be present. But when the electric current disappears, then the magnetic field is going to just not be there. Right? That's it. Now, since I got you here, let's say I'm going to give you a heads up on what we're going to do. Slightly different than last time, but everybody gets the same thing. Let's say we have a inductor here, an inductor instead of a resistor. A coil, inductor, L. Well, what is going to happen? You see, when there is a straight wire, the magnetic field, we close the switch, the magnetic field starts forming again. Current flow, we have electric field, and we have magnetic field. So electromagnetic field. All right. Now, because we arranged that in a coil, and those little spinny circles, those invisible spinny circles, are going to arrange themselves so they're going to feed each other and going to start spinning in unison, just like that. It's going to have magnetic field concentrated. That means it's going to cause a tension. If you have a spring, if you take a pen apart and take the spring from your pen, alright, just spring, put it against the wall and press it with your finger that way, you're going to contract the spring just like that. Right? And then you release your finger from there. What's going to happen to the spring? The spring is going to go, bam! It's going to go how far? It is going to go far. So the normal field of operation within the spring if you just controllably pressing and releasing and but as soon as you suddenly let go of it, that thing is going to shoot 40 feet wherever you won't even be able to find it. We're going somewhere with that, okay? All right. What is going to happen here? That magnetic, because this is a physical, the spring. This is just like a spring, but electrical. So instead of a physical tension with electricity and a coil, we're creating a electrical or magnetic field tension. And as long as the current flows, there is that magnetic field tension. And what the magnetic field tension really does is that because coils do not like change, they hate change, they're going to create a magnetic field around itself that tries to oppose the electric current. So it is going to have certain energy. As soon as you suddenly break the circuit, I'm not going to open the circuit, you open the switch, drastically, suddenly, that magnetic field is going to aggressively collapse, rapidly collapse. And it's going to do electrically same thing as physically that spring would do, spring load or shoot somewhere far. And that is going to create a huge, momentary, short as it is, a voltage spike that goes the other way, in reverse. And that's what we're going to be talking about a little bit today, because there's something extremely important that you need to know that has to do with what I just showed you. All right. What's EMF? Okay, In coils and relays, EMF is induced when current flows through the windings. All right. Current flows through the windings, magnetic field is introduced, tension is introduced, therefore EMF is introduced, or induced, induced, made, right? Created. In the context of physics and electrical engineering, EMF can refer to two distinct but related concepts: electromotive force, and this is a power source, a driver of current, a current pusher. It's going to push the current through the circuit. And electromagnetic fields, which are the combined presence of electric and magnetic fields, but the condition is the current has to flow. If the current is not flowing, then we only have the electric field, electric tension. EMF as electromotive force. Let's see what my blood, sweat, and tears have done some time ago. In this technical sense, EMF is not a force, but a potential difference, which is basically actually voltage, measured in volts, and that EMF is produced or introduced or produced by a source, quite often turning mechanical energy into electrical tension, or by chemical reactions, by the means of chemical reactions. It is the energy per unit charge provided by a source like a battery or generator. That thing here basically complements the same. It's the same thing said in a different way. I'm not going to spend too much time on that line. Relationship to magnetic fields. According to Faraday's law of induction, a changing magnetic field induces an EMF in a nearby conductor. Where is my board? Let's just create another page here. We have a magnet or two magnetic poles, north and south pole, magnetic pole. We have the flux going there with a certain type of strength. It's going to be more tension in the middle here. Or let's say it's a uniform magnetic field going from north to south. And we have a conductor that goes through those. All right. Here's a conductor. If we connect with the wires to, well, let's say a light bulb, and I'm just going to draw the light bulb here. Here's the thread, here is the bulb, here's the connection, here is the light bulb there. So that goes here, and that goes here, and nothing happens. As soon as this magnetic field changes, we're going to have a momentary electric current flowing through the conductor momentarily. Excuse me. Now, if we interrupt this here, there's my eraser. Interrupt that here, and let's say instead of one single conductor going there, if we have a coil of many turns, and connect that here and connect that here, then the electric current with each added turn is going to add the force of the flow within that magnetic field while it changes. If the magnetic field doesn't change, so let's say we have some kind of like a regulator that regulates a magnet that doesn't exist, imaginary regulator. All of a sudden we turn the magnetic field off or pull the magnet away from that, there's a change in it. So for a second we're going to see that light bulb light up and it's going to die out. When we bring it in, the more aggressively, the more rapid, we're going to create more or stronger current momentarily. Okay? Excuse me. All right. So that's what it says here. According to the Faraday's law of induction, a changing magnetic field induces EMF, electromagnetic force, in a nearby conductor. Is going to create a tension from one point to another point in the conductor, actually. This is the fundamental principle behind electrical generators, which you're going to study in electrical machines. Relationship to electric fields. An induced EMF creates an electric field that pushes charges through the circuit. Electrons go one way, positive charges go the other way. This induced electric field is sometimes called non-conservative, meaning that it can do work on a charge moving in a closed loop. Remember, from the scientific point of view, when is work done? A work is done when a certain object is moved a certain distance due to applied force. Yeah. So that's the movement of electrons. The objects are electrons here. Huh? Okay. EMF as electromotive force. As the force. In environmental and health context, we have to touch up on that a little bit. EMF refers to combination of electric and magnetic fields. These fields are invisible areas of energy associated with the use of electrical power. And here's a table. Let's see what the table says. Here's the feature, okay. Electric field in this column, magnetic field in this column, and here's some features here. Okay, electric field is produced by a voltage, electric pressure, the electric tension, difference of potentials. Magnetic field is produced by a current flow. Designations. We designate electric field with E, and we designate the magnetic field with B or H. All right, electric field. Where do we see? When does it occur? How is it become to be? Electric field is present whenever the device is plugged in, whenever the power is supplied to it. Not necessarily when the current flows. As long as the tension is there, the electric tension, difference of potentials, we have electric field. Magnetic field, on the other side, is only present when there is a current flow. Then you have that magnetic field spinning. So the current flow causes the magnetic tension. It causes the magnetic field buildup. And sometimes we use it to our advantage, and sometimes we try to prevent that from happening to other devices. So sometimes we like it, sometimes we don't. Such is life. All right, so now shielding, preventing it from happening or containing it. Electrical field is easily blocked by dielectrics, insulators. Magnetic field is not easily blocked. It passes through things. Most common materials, although you've heard of a Faraday's cage, not going to explain what Faraday's cage is. If you want, research it yourself. What a Faraday's cage is something that will actually is able to block the magnetic field or electromagnetic field. Units. Electric field, we measure that in volts per meter, and magnetic field, Gauss or Tesla. Right. And there's some conversion tables or conversion formulas. You can convert Gausses to Tesla and Tesla to Gausses. Key takeaway points. Let's see here. Stationary versus moving charges. Static charges create only electric field. We just talked about that. Moving charges or current create both electric and magnetic field. Unification. All right. At high frequencies, now when it comes to frequencies, every bracket of frequencies has its own little ways of behaving. Low frequencies behave certain ways. Ground frequencies behave certain ways. High frequencies behave certain ways, a little bit different. VHF, very high frequencies. UHF, ultra high frequencies. Microwaves and light, which is frequencies and particles all together. They all have a little bit different behavior. And over here too. Let's say at high frequencies like radio waves or light, high frequencies, You can punch in Google if you want frequency spectrum, and it's going to give you the whole spectrum analysis of different frequencies and what they're used for and what they're called. So in high frequencies like radio waves or light, these fields are coupled, they're joined. They're together and move together as something's called electromagnetic field or radiation. All right. At low frequencies, like the 60 hertz power lines here in North America, or maybe 50 hertz in Europe and other parts of the world, they can be acting independently. They are not that, as tight together as at higher frequencies. All right, just as a side note, health perspective, since there are organizations like World Health Organization, WHO, and whatever the law of the land is, we happen to be in Canada, so we're mentioning Canada here. So health organizations monitor the exposure. Every little thing radiates. Every little thing that, well, not every little thing, right? Anything that works, is plugged in, that conducts electric current, will have certain amount of radiation. However small, but it will. So the government bodies do monitor that, and they will have guidelines that if you introduce certain type of equipment on the market for the consumers to use, regular people to use, it cannot exceed certain amount of radiation because. So everything radiates, it has to meet the criteria, the specifications of not exceeding certain type of radiation. So I will have to look up what the highest limit is. But the mouse, the computer mouse that you're operating, it does radiate because it conducts current. It just doesn't radiate much. It's kept within the limits. Your keyboard that you're typing on radiates. Your monitor you're looking at radiates. Every little thing that works electrically radiates. All right? Now, over here, while extreme, so that's where the health aspect is, right? So while extreme levels, and if you go into engineering and if you design things, you have to comply with those guidelines, right? While extreme levels can cause biological effects, nicely put. Typically, daily exposure from appliances, regular appliances, and power lines that you walk under generally is considered harmless. I like the word generally here, okay. Alright, as far as the generation of an EMF through the magnetic and electric fields is defined by Faraday's law of induction, and here is the formula. An induced EMF E in a closed circuit is equal to the negative rate, that negative sign is extremely important, negative rate of change of magnetic flux. What is magnetic flux? Is the magnetic field that we care about, that is doing the work for us. Okay, excuse me. And okay, induced EMF E in a closed circuit is equal to the negative rate of change of the magnetic flux, with the letter phi, the Greek letter phi, or phi sometimes, and the B stands for the magnetic field, through the circuit. So change of flux over the change of time times the number of turns. If you want, you can go deeper. I'm not going to go deep into this. I'm just scratching the surface. If you want, you can watch that guy. I don't know who that guy is, but you can watch him. It's about an hour and a half lecture on EMF and synchronous motors and generators. if you want to go deeper into that. You don't have to. We're not going to test you on this in this course. So here, number of turns. More turns, higher voltage, because the EMF adds up with every turn. It doubles. Magnetic flux calculated by the magnetic field times the area that's exposed or covered or participating in the speed of things, like having angular velocity, and depending on the angle of the conductor that's cutting through the magnetic field, we're taking the cosine of the angle. But that's, I'm just giving you that heads up on that thing. I'm just showing you that the bells are ringing. Okay, if you want to find out what church it is that the bells are ringing, you have the direction to follow if you want. All right, but it's not part of this course, that going that deep into the subject. I just need you to know what things are and what we can do with that and why we have to conduct ourselves certain ways. Now, the negative sign represents the Lenz's law, meaning that the induced current creates a field that opposes the change that created that. Okay. Relays. Let's look at the relays. Here's a picture of a relay, and here's a picture of a relay. Here's a kind of like animated picture over there, and here's the one of the bigger relays, 24-volt relay probably. What do we see here? We have the inductor, the coil, wound around some sort of dielectric body, insulator. Inside the coil, there is a metallic rod that once the coil is energized, it creates magnetic field. The magnetic field accumulates and it makes a magnet out of that metallic rod. That magnet can pull another metallic object that is close by, and it just so happened to be that armature here of that switch that is going to move the pole, the common pole. So by the means of the pivot here, when this thing is being pulled, that thing moves up and is going to change the status of those terminals of the relay. Those working terminals. These are the pilot terminals, so to speak. So here's the common terminal or common pole, and it's in the monostable condition. It has one steady state. It's a monostable device, that one that we're looking at right now. There are some latching relays too. This one is not. It's a monostable device. The latching relay would be bistable device, right? Right. All right. So by default, these two are connected. So if you have circuitry connected to that, the current is going to be conducted through that contact, and things will be happening. Right? Now, as soon as you energize that coil, this one becomes a magnet, pulls this one up. This pushes the pole up. That becomes open. This becomes closed. So these two are connected. That's how relay works. When you're working with relays, if you're designing a circuit from scratch, you have to consider specifications such as the resistance, the pure DC resistance, because if you have a lot of wire, you're going to have the resistance is going to accumulate. As far as DC, because we're using DC current anyways, DC voltage in coils. So you need to consider the resistance so you can get enough current to flow, because another thing another spec of the relay is that it's going to be specified in the data sheets of what is the minimum current that it needs in order to make that move, for that switch to happen. So that depends on the resistance of the coil, depends on the power supplied, and so on. Just so you don't get frustrated when you're designing the system it's supposed to work, and it's not. All right, working principle. Whoa, this is what I just said. Magnetic field passing through the conductor induces the electromagnetic force, EMF, at the terminals. All right. So if we pass magnetic field through that, but it also works in reverse. The principle works in reverse as well. Applying voltage across the conductor generates magnetic field. Cool, eh? Around it. Okay, around it. When this conductor is arranged into a coil, it creates a concentrated magnetic flux, which we talked about, with north and south poles. Inserting metallic rod inside into the center of the coil turns it, which means the metallic rod. Should be better, more clear constructed sentence. Turns it into a powerful, controllable magnet. What kind of a magnet? Electromagnet. Which means it becomes a magnet when the coil is energized. When the coil is de-energized, it becomes not a magnet. It's just a piece of metal. And here's the sequence of events: energizing, attracting, switching, and reset. Well, I'm pretty sure we went over that already. Contact configuration, you can just have that here. R for the relay contacts, and on our schematics we have that things designated with letter K, right? RK, same thing, right? In our case. Now we have the contacts. Here's normally open contact. Here's normally closed contact. Here are two contacts simultaneously working with each other. They're both normally open, or they could be normally closed if they're designed that way. Here is a single pole double throw. Single pole double throw. This can go here, or this can go here, or it can go here. So it's in a way, in a sense, this would be a bistable device, unless it's a monostable device if it's supposed to return to certain things. And it actually, in this case, yes, it is a monostable device. It has one default state when it's completely de-energized. All right. So then we have a double pole, double throw, double pole, double throw. So those poles here are synchronized. BM, break and make. Make means make contact. Break means break contact. Right? And you can read down here. Pole, this is a pole. Here, single pole. Double or single throw. So here's that. Normally open, normally closed. C stands for the common terminal. And that's about it. I feel like Baba at Forrest Gump telling him what can you do with the shrimp. All right. There's a nice cute slide here. All right, cool. Let's move to another one. Ooh, this is where things are getting serious here now. Back EMF, and especially back EMF in relays, because relay has an inductor that's energized. What happens when we interrupt the power? When the relay coils are de-energized with current interrupted, turned off, suddenly the collapsing magnetic field induces a reverse high voltage spike. Basically what it is that when the current flows through the coil builds up a strong magnetic field around it that opposes the current flow, but the current is going to push itself through anyways. So that means that the field is going to be there, the tension. The coil is going to work with you, but it's going to be mad at you. It's going to be under tension always. And as soon as you interrupt the power, and it has to be aggressively, abruptly suddenly interrupt the power, then the coil is going to hit you back. And it's going to hit you hard. So you better run, right? Or you can do some other stuff electrically. Why back EMF is a problem? Alright. Because the reverse voltage, as soon as the coil is de-energized, it reverses its polarity and hits you with a hand and hammer. It just smokes you. In a very, very short time, it takes about a microsecond to release a tremendous amount of voltage, which is called a back EMF because it's in reverse. The best analogy here is using a spring. Excuse me. If this is a wall and this is a spring that you just took out from a spring-loaded pan, and if you want to play with it, you push it with your finger. Here's your finger. And you push it that way, and you're going to contract that into maybe that physical size, and you're holding your finger here, not letting it go. What happens if all of a sudden you remove the finger? Just suddenly. That spring, you know what's going to happen. That thing is going to spring back in the reverse direction of you acting on it. And it's not going to go that far. It's going to go ping, and it's going to go on the other side of the room as far, incomparably further than this distance of operation that you're going to perform here. So same thing with the inductors. As soon as you interrupt the power, it springs back exactly the same way. Well, not really exactly the same way, a different way actually, because it's electrically. But the severity of the spring back is huge. It is extremely important for us to know. How can we prevent any damages? Because let's say there is a relay coil here connected to a driver, which in this case is a transistor, BJT, bipolar transistor, solid state, simple as it gets, collector, emitter, base. Here is the positive power rail, here is the negative power rail. There's electric field between them, there's a tension, so this is our supply. The current is going to try to push itself through the resistance of this coil, through the resistance of this transistor, and it's not going to make it because the transistor is going to be not conductive unless you apply a little bit of current flow here to encourage the big stuff to happen. So that's why we need to consider the minimum amount of current, the resistance, the voltage that's there. So that's for the design thing here. What happens if you suddenly interrupt the power? Remember what's happening? The coil reverses its polarity extremely severely in the reverse way, which means this becomes positive. Normally, under normal operation, this is the positive side of the coil, this is the negative side of the coil as it is supplied by the power. When the power is cut off suddenly, that thing reverses extremely aggressively and it shoots high current spike in a reverse way. Whatever it's in its way, it can be damaged or it can be softened, which means it's hurt and it still works, but we don't know how long it's going to work. And usually when those things stop working, it's when we least expect, most inconvenient. Okay, now we have a little different device, another device here. We have a diode, and if you haven't studied diodes yet, but I think you did, diode has an anode and has a cathode, and diode only conducts current only one way, and it's this way, just like the arrow would be pointing, so the conventional current would flow here. So there's to be the positive side, negative side of the diode, and which one do you call it anode, which one you call it cathode? This is anode, this is a cathode. Anode is the positive, cathode is the negative. The way I remember is that the school analogy, what's the best mark you want to get at school? You want to get A+. Associate the plus with the A, associate the A with the word anode, and you remember that for forever now. Right? But look, under normal conditions, this diode is not forward biased, it's reverse biased, so it just doesn't conduct. Here's the positive rail connected to the negative cathode part of the diode. It's trying to push the current this way. It's not going to happen because the diode is reverse biased. It's just directional electrical valve that only goes that way. It doesn't go that way unless you really force it, then you're damaging it, right? Everything has its limits. But under normal conditions, nothing is happening. Current doesn't conduct. But when the diode, all of a sudden, if the relay or the coil all of a sudden just lets go, creates a huge spike in the reverse, then this diode is going to start conducting, and it is going to prevent from the spike going anywhere beyond, because it is going to take the hit, not everything else. So it's called a kickback diode or protection diode or protective diode. Those diodes have to absolutely be installed wherever you're installing a relay. Now, some of the relays have that kickback diode built in, so you have to read the specs. But even if it has the diode built in, and if you install another one, you're not going to cause any problems. All right. How does the kickback diode work? This here says what I just said. So you can read that later once you download this presentation. Applications for the relays. Relay driver circuits, so you can have a smaller relay driving a heavier relay. Cascading things. Solenoids. We have worked with solenoids already. What's a solenoid? How is it different than just an inductor? A solenoid causes physical movement. Like a plunger or a pusher, it's an electromagnet with a rod that sticks out when you apply power. And retracts when you or whatever is designed. And there are different designs of solenoids. And inductors are also used, motors, inductive loads, and all that stuff. Now, solenoid, is that what I said? Just a regular inductor is an electronic component that is being used as an electronic component in electronic circuitry when you need some reactive resistance or make a filter or whatever else that you need, the inductiveness of the inductor. All right. Now let's see how severe is the kickback EMF or the back EMF. Let's say a scenario when a 24 volt DC voltage is applied. Okay, we have 24 volt DC. Once the magnetic field has fully stabilized, the relay, so the magnetic field is going to create tension, and stabilize, doesn't go up or down. The coil acts as a simple resistor. And the resistance of the coil is basically the accumulative resistance of the length of the wire. Alright, mouthful here. Let's then consider here a formula that would be Ohm's law. Remember that one? Alright. There's the calculation. We have 24 volts. And let's say we have 600 ohms resistance across the coil. That's the DC resistance, not even reactance, because we're applying DC voltage here anyways. So what's the current going to be? The current is going to be 24 volts over 600 ohms, and clickety click, you're going to get 40 milliamps DC current. Okay, well, let's see what else we have in store. The steady state current determines the strength of the magnetic field required to hold the relay's armature in the on position. So it's working for us, except when you let that go, you better stand back, so to speak, quote unquote. Back EMF at the switch off. Alright, when the switch is opened, which means the current suddenly drops to zero. Suddenly is the key word here. So that's the delta, or the change of current, delta I, change of current. Because the coil is an inductor, and inductors hate change, it resists this change by generating a massive voltage spike known as the back EMF, or a flyback voltage, because it actually reverses its polarity and shoots back at you. Let's put some numbers. The formula for the back EMF is, well, because it reverses itself, so we have to have that minus here. L stands for inductance of the coil. And here's the change of current and change in time, delta I over delta T. Detailed calculation, apply some numbers. And let's say this thing here happens in 1 microsecond. Or 10 microseconds, which is still huge. Or I mean, huge smallness, if you can say that. So it's going from 40 milliamps to 0 in 10 microseconds. Might seem like not much, but all that change is concentrated in a very, very short time, 10 millionths of a second. It has to be at some price. That means the spike is going to be huge. Alright, so we have the inductance, that's kind of realistic here. 600 ohms, also realistic. 24 volts, definitely realistic. So when you put those numbers into that formula, look what the voltage spike we're going to get, considering, remember, we're still working in the 24 volt DC system, and some of the parts are going to be rated for 100 volts, some of them are 50 volts. You don't want to subject the components to too much voltage because they can get damaged. And what voltage is that 24 innocent looking coil going to give us when it's suddenly switched off? It's going to lash back at you with, and no, it's not a mistake, it's 6,000 volt of a spike. Right? In which way is that going to hit you? In a ringing kind of a way. I want to show you where's my that's not what I'm looking for. That's what I'm looking for. Let me find it. This time I will, because we have a couple minutes here. I know we're going over time, but bear with me. It's for your own good. You paid money, you're getting more for your money. All right, I'm talking too much. 26 winter. Theory. Week 4. That's what I was looking for. See this? That's the door stop to prevent the door from hitting the wall. What happens when you hit it with your foot? This thing goes, right? That's what I was. See, I spent so much time just to show you this. And that's electrically the same thing. It's called a ring. It's ringing. Now, if the ringing is supplied by a certain amount of continuous power going on, you can have an oscillator. But if it's just hit, just like the brass church bell is hit with a hammer, it rings and it dies out. So the same thing, it rings and it dies out. Except the initial spike is 6,000 volts. Right over here. Oh yeah, here's the special effect for the last slide. But I'm going to have something for dessert again. But wait for the special effects first. Okay, ready for it? Alright, good. Yeah, special effects. Now, I have multi-simmed something just for you. What do we have here? Come on. Alright. Open the switch. Simulation is not on. We have a power supply, DC power supply, and this time 12 volts. Why not? We have a current probe here. Switch. Single pole, single throw. And we have an inductor with the inductance of 3 Henrys. Let's take some of the specs here. It's this one has a 300 ohm coil resistance. 3 Henrys. It's also a realistic type of inductor. And I connected a oscilloscope to the coil right here. And the other side of the oscilloscope is connected to the ground, so this is going to display exactly the voltage, what is happening across the coil. And when we turn the switch on, it should not show more than 12 volts, right? Actually, it should show almost exactly 12 volts. So let's see. Turn the simulation on. So this is our zero reference. It's a slow moving beam that I chose it purposely. Look what happens when we turn the current on. That thing should jump up. Oh, look at that, it did. So now we are sitting at 12 volts. Not a very spectacular thing, is it? However, look what happens when we open the switch. Remember, that coil is going to reverse with a huge spike. See if I can catch that spike. If not, I will do it a couple times. Oh, look at the spike here. Whoa. All right, let's try it again. Another spike. That thing goes off the scale. Of course it's going to go off the scale when we de-energize. There you go, see? Now, I'm going to try to catch that by doing something that's called a single shot on the oscilloscope. So I'm going to close the switch. And it's going to be a little bit tricky, but I was successful last time. Where's the single shot? Man, okay, here it is. Here, good, got it. And now it's frozen on the screen. And if I play with the time division adjustment, I can stretch that in time. I can magnify and see if it actually shows as a ring in a small amount of time. Oh, it does, doesn't it? It's a ring. Multi-sim is kind of quite realistic that way. All right. So that is why we need to have something that's called a protective diode, otherwise called kickback diode, and I just happen to have one sitting here behind the oscilloscope, so you couldn't see it. So I'm going to stop the simulation and put that diode in reverse parallel to the coil and see if we can smooth things out. Connect this here, connect the anode here. So normally the diode is biased in reverse. It's just like not being there, kind of, ideally, right? But it does its job when things are turned off. It's supposed to take the hit. Let's see if it does. Simulation on. Switch on. Oh, wait a sec. I should unstop the oscilloscope and make it go slow again. There we go. Here's the beam. Close the switch. Things go up to 12 volts as they should, and they did. Now, according to what I said, we should have no spike because the diode's going to take the hit. Oh, look at that. Nice and clean switch down. No spike. See? It's not an option. The diode, every time you install a relay or inductor, solenoid, and things like that, the relay has to be there. But in a lot of cases, the diode has to be there, and the diode quite often is built in to the device. Cool. I hope it's going to be useful for you whenever you get a job somewhere, or maybe you're going to find yourself a situation that you can impress somebody at the bar. Either way you want to use it, go ahead. Thank you so much for your attention. We still have participants going on here, and I will see you tomorrow during the lab. Thank you for the attention, and of course you are wonderful. All of you are special, but not as wonderful as me. With that happy note, thank you and good night.